For just a second, imagine a bridge. Bridges are amazing. Thousands of people rather walk on it, ride their bicycles on it, or drive on it every single day for different reasons, whether it be to get to work, whether it be to visit a friend, or even for pictures. But have you ever wondered how it was built? Now, we can talk about the engineering aspects of a bridge, like all the forces involved and all the types of materials needed. But at the basis of that, what made this monument achievable? To answer that is everyone's favorite subject, math. Hello, everyone. My name is Alex Castro, and this is my project for Math 472. As we know, math is the study of numbers, shapes, and patterns. It is extremely important it is an extremely important and powerful tool in our lives, and we often use mathematical concepts more often than we even realize it. It is the building blocks of everything we know and serves useful to so many real life applications, from business to medicine, or from psychology to engineering. For example, I remember when I was a sophomore in high school, in my trig class, I raised my hand to ask my trig teacher, when am I ever going to use this in life? To which she responded, never. Fast forward 6 years, and I'm a senior mechanical engineering student about to graduate with a concentration in applied mathematics. So, more of the story is life is crazy. But either way, math has many real world applications. One of those particular applications is the ability to be able to model system behavior or interaction between two things. The application and topic for today is love affairs. I'm sure we're all familiar with what they are. Simply put, love affairs are romantic or sexual relationships between two people, especially one that is outside of marriage. There are many reasons for love affairs, and some people have an affair because they believe their needs aren't being fulfilled, whether it's emotionally or physically, or maybe they're experiencing financial troubles, or even one person might be facing a lot of stress and tiredness from work. But we aren't psychologists, and the human mind is not what we'll be studying today. Today, we will be taking a look at a particular love affair, the love triangle and mindset of Scarlett O'Hara between Ashley Wilkes and Rhett Butler in the book Gone with the Wind, written by Margaret Mitchell. So this book takes place in the American South during the days of the American Civil War and Reconstruction era. The book tells us the story of Scarlett O'Hara, a strong-willed but stubborn daughter of a plantation owner. While the book has many other themes, her love life is one of them. Scarlett is defined as a very beautiful woman who has been receiving many offers of marriage, but only has her heart set on Ashley Wilkes. The two grow fond of each other, but soon after they become a married couple, Ashley realizes that they are not compatible because of Scarlett's high demanding temperament. They soon divorce, and once Ashley remarries with another girl, Scarlett starts to like him again. Then, let's fast forward a couple of years, Scarlett meets Rhett Butler, an older man who behaves much like herself, and after some years, they marry as well. The marriage starts out fine, but their similar personalities cause them to clash a lot. And at the same time, Scarlett cannot forget about her first love, who was Ashley. Rhett soon decides to leave her, only for Scarlett to change her mind and realize that Ashley, her first love, was only a silly crush and falls back in love with Rhett. Overall, there was a lot of going back and forth in Scarlett's mind about what exactly she wanted. But the key thing here is that for a while, it seemed as if nothing was going right and that Scarlett would never finally settle with anyone. So upon some research, mathematicians have described the modeling of this behavior as a Romeo and Juliet model. Equations are just mathematical ways of looking at relationships. Similar to the story of Gone with the Wind, the story of Romeo and Juliet shows many similarities, and a model can be constructed to show the love life of the two. So, from Romeo's point of view, the more that he thinks that Juliet is into him, the more he begins to like her. Likewise, the more that he sees that Juliet is disinterested, the more that he becomes disinterested. From Juliet's point of view, the more Romeo displays his affection for her, the more Juliet stands down. But as Romeo begins to give up, Juliet begins to display affection. And well, you can see that this turns into like a never-ending cycle that just continuously repeats. Now, you may be asking, what do these love affairs or relationships have to do with math? Well, we can actually model this love story as a nonlinear system. So, what is a linear system, though? Well, as we know, we come up with some linear equations, and all the terms have an exponent of 1 and take on a form similar to y equals mx plus b. However, sometimes equations can be written with two dependent variables as shown below. This is a two-dimensional linear system. These two equations can then be represented as a matrix function. Just like any set of equations, a solution can be found. And when we do find these solutions, sometimes these two functions can intersect, or sometimes the solution can include when we find the roots of a particular function. In these cases, the solutions refer to something called a fixed point. These solutions can be visualized as trajectories or lines drawn on a graph that can describe a future position from a given initial condition. Here we will take a look at what we call a phase point, which are a bunch of trajectories in one plot. These solutions to the following matrix, to a matrix, can then be expressed in the terms of the equation below, with where C1 and C2 are based upon initial conditions. So now, using the definition of trajectories, these solutions can then be visualized as moving lines, which again results in a vector field or phase plane as shown to the right. In this figure, there is one main important thing. One is that there is a point at the origin where it seems like everything revolves around. This is what we call a fixed point, and ultimately it's the solution to a particular equation. If we were to fill these lines in, these trajectories would form closed orbits, creating a phase plane as shown here. But the question is, what does this tell us? Well, the fixed point corresponds to a point of stability, and while the closed orbits refer to a behavior of oscillation. You see, it keeps going, and it could possibly tell us a story. So let's take a look at other examples of phase portraits. Say we have two equations, x of t and y of t. So when alpha varies, the following phase portraits are shown. So when alpha is less than -1, x of t, as shown to the right, decays more rapidly than y of t. Taking a look at the trajectories, as we approach the origin, the vectors that are coming in from the sides, which are represented by x of t, are declining very fast. Meanwhile, y of t decays slower. Now, if we have the case of alpha is greater than -1, but less than 0, we can expect the opposite to appear. As the trajectories approach the origin, y(t) decays exponentially faster than x of t. One thing to note is that in these two plots, they have one thing in common, which is the fixed point. Notice how all the trajectories lead into the fixed point. This is what we call a stable node. Now, if we take a look at the case of alpha being greater than 0, this is what results in. This fixed point becomes unstable since x of t is experiencing exponential growth in the opposite direction. However, since we still have y of t heading to the origin, this one is actually classified as a saddle point because it's almost in a way facing a transition phase. But if y of t was facing away from the origin, then this would just classify as purely just an unstable node. So these were just a couple of examples for visual purposes. One important thing to note in this slide actually is that if we go back to the matrix that we had in the beginning, this matrix included 2 zeros. So all these examples were done under the condition that the matrix included 2 zeros. But what if there were any random numbers that didn't include 0? In that case, we could achieve something similar to the general solution as mentioned before, but with a twist. In this case, we'll get an equation as shown below, x of t. And with this, the first thing that we would want to do is to find the characteristic equation which can be found by taking the determinant and the trace of the matrix. We can then solve for the roots, or in this position, we call it the eigenvalues, which are the solutions. After finding the eigenvalues, we can find the eigenvectors and putting everything together to give us the bottom equation. Obviously, the C1 and C2 would have a value depending on the initial condition given. So using this information acquired, I'd like to introduce limit cycles. So limit cycles are closed trajectories in a space that corresponds to oscillations. There are neighboring trajectories that are not closed and either spiral away or into the limit cycle. They're used to model oscillating behavior, such as the love affairs that we have spoken about, or even with outside influencer variable. And even if there was some outside interaction, it would always return to normal. For example, if you're just sitting down, for example, myself, I'm just giving this presentation, my heart is at a constant, good, regular pace. But if I were to get up and exercise and run a mile, then my heart rate would increase. But eventually, as I calm down, my heart rate will come back to normal. So similar to previous examples, limit cycles can be stable, unstable, or semi-stable, as shown below. Limit cycles are nonlinear and closed orbit, and being closed orbit will tell us if there is a repeating pattern. But how do we know that the limit cycle has a closed orbit or not? Well, one of the ways is that we could find out is by using Dulac's theorem. Simply put, Dulac's theorem tells us that for a function x dot, there is a continuous differential function g of x that when multiplied by the original function and then taken the derivative shows that it is positive everywhere. If it is positive everywhere, then there are no closed orbits. Mathematicians usually use this continuous differential function g of x as the function shown below. So let's get into the love affair. So let's model the love relationship between Rhett Butler and Scarlett O'Hara. Suppose that R dot is portraying Rhett's mindset and S dot is showing Scarlett's mindset. The terms AR, AS, and K are positive. But what exactly does this whole thing mean? Well, the terms negative R and negative S signify that the more love Rhett or Scarlett have for each other, the faster the love for each other decreases. AR and AS are baseline amounts of love that one has for another. When Rhett does not have any affection towards Scarlett, Scarlett will begin to show signs of love, hence the AR. This is the same in the opposite situation. The terms KR e to the negative R and KS e to the negative S are zero when R and S is small or large. So remember that R and S symbolize the love that they have for each other. Too little love has no effect. And likewise, a great amount of love in this situation in one partner will cause the other partner to sway away. Seems frustrating, right? It kind of seems similar to those two people in high school who you knew liked each other, but neither made the effort to ask the other out. So as you could tell, it seems like Rhett and Scarlett are just not meant for each other. So we can apply Dulac's theory to prove that there are no closed orbits, or that there is no such thing as a period solution in this example. Remember, we have mentioned that mathematicians state that you can use any of the following functions. So we could use g of x equals 1. First, we multiply the original functions by g of x, which essentially results in the exact same thing. From this, we can take the partial derivative. R dot is derived with respect to R, and S dot is derived with respect to S. Therefore, they both result in -1 or a total of -2. This implies that the region RS is bigger than 0, therefore no periodic solutions exist. So there might be a chance for Rhett and Scarlett to actually meet in the middle and be happy. So finally, we can plot a certain situation. So let's say AS and AR who are constants. We assume AS is 1.2 and AR is 1. Let's also assume that R dot and S dot are 0. So what that means is that when Brett and Scarlett meet, they are both indifferent to each other. So this would result in the following figure, which would actually model the first stage in the relationship. Since we assume that they did not fall in love at first sight, they were able to grow and eventually become to a stable fixed point. Ultimately, we can plot many versions of the story, but for this one, for example, just helps prove that in the end of the book, Gone with the Wind, that they do end up happily ever after. So in conclusion, math has many wonderful applications, and I was even shocked to know that we can model love relationships. The power of dynamical systems is real and wonderful. So I'd like to conclude my presentation and thank you all for listening.